All right, so in this section, what we're going to talk about is the unit circle. And before I introducing the unit circle, I want to just touch base a little bit on it. Let me give you a little information on it. A unit circle, it has a radius of 1, and its center is at the origin on the coordinate plane. Okay? Well, these values that we see here on this unit circle, they're not random. They're corresponding to something specific, and I actually want to visit that concept for a second. And I'm going to take a look at triangles. What are the two special right triangles that we have? Okay, that's right. So we have a 30, 60, 90 triangle, and we have a 45, 45, 90 triangle. So let's take a look at our 30, 60, 90 triangle. Where does that come from? All right, so let's explore an equilateral triangle. In an equilateral, we're going to pretend this is obviously not drawn to scale. In an equilateral triangle, all the angles are congruent, so that would be 60 degrees, and all the sides are congruent. So for the sake of this example, let's say all sides are 2. And then I'm going to drop an altitude. When I drop an altitude, I create a 90-degree angle. It bisects this angle in half, so it ends up being 30 degrees. So this is now 30 degrees. This is 60 degrees. But remember, I took this side, I put a bisector through it, I cut it in half. So this triangle that I'm outlining in red, this side is now 1, this side is now 2, this side is unknown. How do I find that x, that unknown? The Pythagorean theorem, okay? So that would be x squared plus y squared, or if you want, a squared plus b squared equals c squared, so c squared. So x squared plus 1 squared, which is 1, is equal to 2 squared, which is 4. Subtract 1, I'm going to get x equals root 3. Notice that it's just positive because we're talking about distance here. So this side is root 3. So now I can actually start identifying what you guys pointed out, that SOHCAHTOA, sine of 30 degrees, the cosine of 30 degrees. Let's actually go ahead and explore that a little bit before I put this triangle away. So let's find the cosine of 30 degrees. Remember, that's opposite, so that's going to be 1, over hypotenuse, which is 2 here. Remember, here's our hypotenuse, so that's over 2. So the cosine of 30 degrees is half. Does that make sense to everyone? Okay. And then the sine, God bless you, of 30 degrees would be something similar here too. Let's take a look at a 45, 45, 90 triangle. Okay, so let's duplicate that triangle. Let's put this away for now. A 45, 45 triangle is what kind of triangle? An isosceles right triangle, yes. So these sides are congruent, so for the sake of this example, let's make both of those sides 1. And now I can find that hypotenuse by using the Pythagorean theorem. A squared plus b squared is equal to c squared. So 1 plus 1 equals c squared. So take the square root of that, which is going to be root 2. Notice that I'm keeping just the positive side, the positive solution. Why? Because we're talking about distance here. So my hypotenuse is 2. So if I wanted to find the cosine of 45 degrees, okay, cosine adjacent over hypotenuse. So once I simplify that, I'm going to end up with root 2 over 2. Does everyone agree? And then I can continue that. I can find the sine, the cosine, the tangent. Now let me draw your attention to this wonderful unit circle. Okay, I want you to notice that the same solutions we were finding, half, root 2 over 2, root 2 over 2, that's on the unit circle. Okay, let's actually overlay these triangles in here. Here I could put my 45-degree triangle inside it. So you see me trying to insert it. Obviously it's not drawn to scale, but I can overlap these right triangles in there because these triangles exist within that. So here is your 45-degree triangle, 45, 45. And now I can evaluate SOHCAHTOA there, and I should end up with these same values that I have right here. The same thing happens if I were to do, let's say, a 60, 30, 60, 90 triangle. Here's 60 degrees. this is 60, this is 30, and I should end up with these values if I were to evaluate my triangle. So that's where some of these values are coming from. So it's not random. These angles aren't just corresponding to random points. They're evaluated from our trig ratios. Remember SOHCAHTOA. Sine is opposite over hypotenuse. Cosine adjacent over hypotenuse. Tangent opposite over adjacent. All right, so the 6 trig functions. If I'm looking at the unit circle, I can evaluate my trig functions here. Something to keep in mind, sine of an angle is always going to be y on the unit circle. Cosine at the angle is always going to be x. Tangent is always y over x. Cosecant 1 over y. Secant 1 over x. Cotangent is x over y. So if I'm using the unit circle, notice that if I'm looking at particular points, I can evaluate my trig ratios based on those definitions of triangles, points on the unit circle, and I can tie it all back together. So it's not random. What I mean by this, let's look at our unit circle, okay? So here's our unit circle, and let's take a look at an angle. Let's look at pi over 6, and pi over 6 is going to correspond to 30, and we should be able to convert that back and forth, right, between radians and degree measures. So let's take a look at cosine at pi over 6. Well, according to the slide I just showed you, cosine is the x, sine is the y. So you should write that somewhere. Cosine always corresponds to the x coordinate point. Sine corresponds to the y. I like writing it as a coordinate point so that way I don't forget that cosine is x, sine is y. So cosine at pi over 6, what's the x at the coordinate point I circled? What's the corresponding x here, guys? Square root of 3 over 2. That's cosine at pi over 6. What's sine at pi over 6? Remember, sine is your y. A half. Tangent at pi over 6 is your y over your x. So now you have to put y over x. You have to simplify the fraction. You're going to rationalize that denominator. What do you end up with? Good, root 3 over 3. And then I can find my reciprocals. Let's go ahead and find our reciprocals. Let's actually minimize that just a tad. Let's find our reciprocals for cosine. Cosine, the reciprocal is secant. Okay? Remember, I could technically do 1 over x here, but I don't have to do that because I already evaluated this. So secant at pi over 6, all I have to do is flip that over. So 2 over root 3, I need to rationalize my denominator and end up with 2 root 3 over 3. Cosecant is the reciprocal of sine. So flip over what I have there. What's the reciprocal of half? 2. The reciprocal of tangent is cotangent. Flip over root 3 over 3. Or flip this guy over and you end up with what? Root 3 over 2 over a half. What do you end up with? Root 3, because the 2's, they reduce. So that's our answer. We just evaluate all 6 trig functions at this angle. So technically, if I asked you to find, I can do this across the board, any unit circle value. Let's take a look. I can, if I wanted to do, what is the cosine at 7 pi over 4? Root 2 over 2, it's the x. What is the cosine at pi? -1, good. What is the sine at pi over 3? Root 3 over 2. So we're just evaluating it based on the points. I'm looking at x for cosine, y for sine, tangent, y over x, and then my reciprocals, just flip them over. Okay? All right, so let's take a look at this first example. It says, use the figure at the right to find the trigonometric functions at t. But notice that point. We've seen that point before. Half root 3 over 2. Where's that point coming from? It is right here from the unit circle. A half root 3 over 2. Okay? We're essentially evaluating the 6 trig functions at pi over 3. So let's go ahead and do that. Let's put that away. So now I'm evaluating, but here in this diagram, it just calls it sine of t or cosine of t. So cosine of whatever this is. So we're assuming that we don't know, but looking at our unit circle, clearly it's pi over 3. Okay? We're going to label whatever the picture labels it. It labels that angle t. So cosine of t, what is that, Miriam? Yes, it's a half. Now let's evaluate the sine at t. Root 3 over 2 is correct because it's our y. And then we have the tangent at t. What is that answer? Okay, Stephania? Good. It's y over x, so I put root 3 over 2 over half. That's correct, and that reduces to square root 3. And now I can just start finding my reciprocals. The reciprocal of cosine is secant of t, so flip it over, you get 2. The reciprocal of sine is cosecant. Flip it over, you get 2 root 3 over 3. Remember, rationalize that denominator. The reciprocal of tangent is cotangent. Flip 3 over, you're going to get 1 over root 3, but you need to rationalize that denominator, so you're going to end up with root 3 over 3. All right, this example says to find the point xy in the unit circle that corresponds to the real number t. So let's take a look at our unit circle, okay? All right, so here's our unit circle. We're identifying 2 pi over 3. 2 pi over 3 is right here. So now I want to find the point that corresponds to that on the unit circle. That point is negative a half root 3 over 2. Okay, so it just wants you to identify the point that corresponds to it. So your answer for example 2 is negative 1/2 root 3 over 2. But you guys know that I'm not going to give you the unit circle and ask you to identify points. I'm going to tell you what point corresponds to 2 pi over 3 without looking at a unit circle. So you need to know that. So how do you do that? Let me tell you how you do that. All right, so in order to answer that question, let's just look back at the unit circle one more time and evaluate something. Okay, I want you to notice the pattern here. What is going on with all the intervals of pi over 3? So there's pi over 3, there's pi over 3, there's pi over 3. What are the similarities between everything that I just circled? All right, like you just pointed out, the coordinate points are identical with the exception of the signs. Okay, therefore, if I remember that pi over 3 corresponds to this coordinate point, and depending on which quadrant I'm in, I'm going to assign the sign. In quadrant 1, remember everything's positive, x and y. In quadrant 2, x is negative, y is positive. In quadrant 3, x and y are negative. In quadrant 4, x is positive, y is negative. So if I know this point, I can evaluate any interval of pi over 3. I just need to figure out what quadrant I'm in. Well, remember previously we talked about the following. Okay? We said, let's just draw, when we start going around a circle, we start 0 degrees or 0 radians. And then up here on the positive y-axis, we're at pi over 2 or 90 degrees. Here on the negative x-axis, I'm at pi. Here at the negative y-axis, I'm at 3 pi over 2. And then when I make a full cycle, I'm at 2 pi. Now that I'm making my radius a specified distance of 1 unit long must be at 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And now I just need to remember, again, pi over 3 is corresponding to this coordinate point always. I just need to figure out where is 2 pi over 3? 2/3. Well, this is a half, and this is 1, right? 2/3 is greater than a half, but less than 1. So 2 pi over 3 must be in this coordinate point, and that's how I would answer that question. So now I know that 2 pi over 3 is in here. It corresponds to this point on the unit circle. And in this quadrant, x is negative, y is positive. So if I were going to evaluate that point for the 6-trig functions, that's what I'm using. So all I needed to know was this. I then just determine which quadrant you're in because they're consistent, right? I just showed that to you in the unit circle. All right, let's take a look at this example. It says evaluate, if possible, the sine, cosine, tangent of the real numbers. So now we're not looking at our unit circle anymore. Okay, we're in intervals of 2 pi over 3. We already know that pi over 3 corresponds to half root 3 over 2. We established that 2 pi over 3 is in quadrant 2, therefore x is negative. And now I can evaluate my sixth trig. Actually, just want sine, cosine, and tangent. So now I can find the sine at 2 pi over 3. What is that, Lockwood? Yes, it's your y coordinate. It's the y here in the coordinate point. So that's going to correspond to root 3 over 2. Cosine at 2 pi over 3 is what? Yes, it corresponds to the x in that coordinate point, which is negative a half. And then the last one we were asked to evaluate is the tangent at 2 pi over 3. And that's your y over your x, so we're doing root 3 over 2 over negative 1/2, which reduces to negative root 3. All right, remember we're evaluating sine, cosine, and tangent for these values. So now I want to evaluate sine, cosine, and tangent for 6 pi over 3. However, I notice that this can reduce. So what does t reduce to? 2 pi. Okay, remember 2 pi, 2 pi, when I go around a cycle, here's 0, and then I come back to 2 pi, and on the unit circle it corresponds to 1, 0. Okay? So now I want to find the cosine at 2 pi. What's the x there? 1. Good. What's the sine at 2 pi? 0. Good. What's the tangent at 2 pi? 0 over 1, and that's 0. Good. All right, here's pi over 3 again. Do not look at your unit circle to evaluate. Okay? Think back. I said memorize this and this point. I said memorize pi over 3 corresponding to 1/2 root 3 over 2. I know this is one rotation, but it's going in the negative direction, so that's clockwise. Therefore, if I'm doing negative rotations, this is 0, this is negative pi over 2, this is negative pi, this is negative 3 pi over 2, and then back here is going to be negative 2 pi. Pi over 3 must be in here. Therefore, what's negative from that coordinate point now? Okay, the y is the negative 1. So now I can evaluate sine, cosine, and tangent based on this point that I identified. So cosine at negative pi over 3 is what? What's the x there? Half, good. Sine at negative pi over 3 is what there? Negative root 3 over 2. Tangent at negative pi over 3, remember you're putting the y over the x. This reduces to negative root 3. All right, so now let's think about the domain and range of what we've been talking about. So for sine and cosine, I can put any angle I want, right? I can evaluate 30 degrees, 60 degrees, 360, 420, then I can start going in the negative rotation. So notice that I'm inputting all real numbers in there. So the domain is the set of all real numbers. Your output, however, on the unit circle, notice that we were getting fractions, or the largest value on the unit circle was 1. The smallest value was negative 1. So for sine and cosine, the domain is the set of all real numbers. The range is from negative 1 to 1. Why? Because the input is always the angle, and the output is always the point on the unit circle. So sine and cosine are periodic. After you go around one time on the circle, you start repeating those same values. The solutions will repeat from the points on the unit circle. So that's why we say that the period is 2 pi, because they're periodic, they're repetitive. They cycle and give you the same solutions. All right, so in this example, it says to evaluate the trig function using its period as an aid. Well, if I know that sine repeats after a cycle, after 360 degrees, or after 2 pi, if I take away a complete cycle, I will have the same answer. So I want to take away as many complete cycles as possible. So I'm going to take away 2 pi. With a common denominator, that's what? 12 pi over 6. I mean, I end up with sine at pi over 6. I'm telling you that the solutions for sine at 13 pi over 6 are equivalent to sine at pi over 6. Why? Because if I were to graph it in standard position, here's pi over 6. Let's pretend that's pi over 6. And here's 13 pi over 6. One cycle plus that. Those are what kind of angles? Coterminal angles. Same initial side, same terminal side, but different degree measurements. That's why they end up with the same point on the unit circle, okay? So that's why the solutions are the same. Sine, all right, here's another one, guys. Pi over 6 is going to be the reverse of pi over 3. Remember pi over 3 was a half, root 3 over 2? Pi over 6 is root 3 over 2, a half on the unit circle. And that's true for every interval of pi over 6 on the unit circle. So if I know this one, I know them all. I just need to figure out which quadrant I'm in. Here I'm in quadrant 1, and I know that because I drew my picture here. And sine at pi over 6, which one's the sine, the x or the y? The y. Okay, so my answer is a half. All right, so here's our unit circle. Remember what I said to you guys, that you just need to know pi over 6 corresponds to this coordinate point, root 3 over 2, a half. Notice that it's reversed to our pi over 3 friend, so it makes it easier to remember. Okay, and take a look at all your intervals of pi over 6. They are identical. Pi over 6 is right there, pi over 6 is here, pi over 6 is here. The only difference is the signs. So if I know this guy, it makes it easier to identify this one, and this one. All right, and the next one, we're using the period to help us identify cosine at 5 pi. Remember, we want to take away as many cycles as possible, so I'm going to take away 2 pi. But what happens when I take away 2 pi? I end up with cosine at 3 pi. Do I still have 2 pi inside 3 pi? Yes, so you have to take that cycle away as well, and then we end up with cosine at pi. Remember, cosine at pi, if we're just drawing our coordinate plane really quickly, let's sketch it to make sure we remember it. 0, pi over 2, pi, 3 pi over 2. And if we're on the unit circle, that means I'm 1 unit in this direction. That's negative 1, 0. And cosine is our x, so my answer is negative 1. So I will get the same solution whether I do cosine at 5 pi, cosine at 3 pi, or cosine at pi. Therefore, if I get the easiest one, it's obviously a lot easier to evaluate.